In this video, we're going to talk about limits as x goes to infinity or negative infinity. We previously discussed how to evaluate limits as x goes to infinity or as x goes to negative infinity using a graphing approach. However, we can discuss how to evaluate these types of limits without using a graphing approach every time. To discuss how to do this, we'll look at some graphs. It's not important to know the numbers of the scenarios that follow. So I'll be talking about scenario 1, scenario 2, etc. You don't have to know which scenario is which, as long as you understand the principles and can apply them. So in this first scenario, imagine we're graphing the curve y equals a to the x, and a is a positive number less than 1. So for example, y equals 1/2 to the x. We know the graph looks roughly like that, and we can tell intuitively that the limit as x goes to negative infinity of that function is equal to positive infinity, and we can tell the limit as x goes to infinity of that function is equal to 0. The y coordinate is going to get infinitely close to 0 as we move infinitely far to the right. Okay? Now, what if we have y equals a to the x and a is greater than 1? So for example, suppose y equals 2 to the x. Well, if that was the case, then we can see that the graph would look like this using grade 11 concepts, and we know that the limit as x goes to negative infinity of a to the x is 0. As we go to the far left, our y value will get infinitely close to 0, but as we go to the far right, our y value will get infinitely high. And so we can make the two statements shown in red on the right. And those will be the case anytime the base of the exponential is greater than 1. What if a actually equals 1? Well, that's kind of a silly example, but we could say y equals 1 to the x. It would just be a straight line, and we would be able to say the limit as x goes to negative infinity of that function is actually equal to 1, and the limit as x goes to positive infinity of that function is equal to 1 as well. Now, we're not going to deal with any cases in this course where y equals a to the x and the a is less than 0. In other words, where the base is negative. Okay? Let's switch our attention, though, now to polynomial functions. So suppose, so we won't talk about exponentials here, but we'll talk about polynomial functions like x squared, x cubed, etc. Suppose we have the function y equals x to the a, and a is greater than 0. It's possible a is in between 0 and 1, so an example would be x to the 1/2 or x to the 1/3, something like that. If that's the case, then the graph of the function is going to look something like this. Let's use x to the 1/2 for a moment. We're all pretty familiar with that one. Well, as the limit, here we'll write it on the next one, we'll see that the limit as x goes to infinity of x to the a actually equals infinity in that case. As we go infinitely far to the right, our y value will get infinitely high. Now, it's possible a equals 1. In other words, it's possible we're talking about the function y equals x to the 1, and that's just the same as y equals x. And so, we see the curve there, and we'd be able to say that the limit as x goes to infinity of x to the a is infinity. And it's also possible that a would be greater than 1. So imagine you had something like y equals x squared or x cubed. Well, as we go to infinity, we might not know necessarily what's going on the left side of the y-axis, but to the right of the y-axis, no matter what, x squared, x cubed, x to the 4, etc., the function goes up like this, and so we learn that in polynomial functions. So as we go infinitely far to the right, our y value is going to go infinitely high. Okay? Now, putting all those cases together, we can see the following. If a is greater than 0, then the limit as x goes to infinity of x to the a equals infinity. But the limit as x goes to negative infinity of x to the a needs to be addressed on a case-by-case basis. What we mean there is if we were talking about y equals x squared, we would know we have a parabola, and as we go to, as our x value goes to negative infinity, our y value would go to positive infinity. But if we had y equals x cubed, and we wanted to look at the limit as x goes to negative infinity, we could say as x goes to negative infinity, y would be going to negative infinity. So we would have to address this concept on a case-by-case basis, but we would not have to address this concept on a case-by-case basis. That one would be true no matter what, as we showed on the previous few slides. Now, suppose we're talking about y equals x to the a and a is less than 0. So for instance, suppose we're talking about y equals x to the negative 2. To do a little bit of a deep dive on this, you might have learned in advanced functions that one way of doing this is you could graph the curve y equals x to the negative 2 is the same as 1 over x squared. And so one way of graphing that is to graph y equals x squared and then find the points where your x value, where your y coordinates are equal to 1 or negative 1, and then draw the actual curve that results by letting your, having a vertical asymptote there and having a horizontal asymptote along the x-axis. And you would see there, based off of that, that as we moved infinitely far to the right, our y value would be getting infinitely close to 0. Okay, so we can make a general statement that if a is less than 0, then the limit as x goes to infinity of x to the a equals 0. But similar to how we described last time, I won't do the deep dive on this one. The limit as x goes to negative infinity of x to the a would need to be addressed on a case-by-case basis. And finally, if we had y equals x to the a where a is 0, that would be like saying y equals x to the 0 would be like saying y simply equals 1. But technically, x is not allowed to equal 0 in that case because you can't have 0 to the 0. So we would actually have a horizontal line at y equals 1 with a hole at x equals 0, and we'd be able to make this two statements that you see there. Okay, so let's put this into practice. What do you say? Let's evaluate the limit as x goes to negative infinity of 6 to the x over 7 to the x. Well, one thing we can do is say 6 to the x over 7 to the x is equal to 6 over 7 to the x. Instead of having a couple of different x's, let's let's only have one x, and we can do that as you see there. That sometimes takes people a little bit of a moment or two to consider, but think about it this way. If I gave you 6 over 7 and said we'd squared it, you would know that that is the same as 6 squared over 7 squared. So similarly, if I gave you 6 squared over 7 squared, you would be able to say that's 6 over 7 quantity squared. So if I give you 6 to the x over 7 to the x, hopefully you can say, oh yeah, that's just 6 over 7 to the x. Now, on one of our scenarios earlier, we said, well, anytime you have a y equals a to the x where a is less than 1 and it's positive, you're going to be able to say the limit as x goes to negative infinity is infinity. So the answer to that question is infinity. Now, what if we wanted the limit as x goes to infinity of 6 to the x over 7 to the x? Well, it's the same curve, same process. But now, instead of looking at the limit as x goes to the far left and saying it goes, the y coordinate goes to infinity, we're looking at the limit as x goes to the far right, and that y coordinate's getting infinitely close to 0. Okay. So when we are evaluating a limit as x goes to infinity or to negative infinity of a rational function, a polynomial over polynomial, we can do the following. Determine the degree of the numerator and the degree of the denominator, and then factor x to the n from both the numerator and denominator, where n is either the greater of those two values or the lesser of those two values. And if the degree of both the numerator and denominator is the same, then n will be equal to that degree. Factor the same term from both numerator and denominator, then cancel out like factors. We don't have to worry about canceling out zero factors because x is going to infinity or negative infinity, so x to the n will not be 0. Then in step 2, we're going to determine the limit of each term and of the numerator and add those limits. We'll determine the limit of each term of the denominator and add those limits. Then what we're going to be able to say is if we have a numerator with a limit that's finite, over a denominator growing without bound, that would produce a limit of 0. So 2a means you have a finite number, like let's say 3, over a denominator that's getting infinitely large. That's going to go to 0. It'll never equal 0, but the limit will be equal to 0. If that's confusing, think back to the little boy who walks halfway to the wall with each step. He never gets to the wall, so he never equals the wall, but the limit is the wall. The wall is definitely serving as a limit. So if we have a finite numerator over a denominator that's getting infinitely large, the limit is 0. Now, if we have a numerator with a limit that's finite over a denominator with a limit that's finite, then we'll have the quotient of those two limits. So if we have a numerator that has a limit of 3 over a denominator that has a limit of 4, the answer will be actually 3 over 4. For part C, if we have a numerator with a limit that's finite over a denominator infinitesimally small, that'll produce a limit of infinity or negative infinity, depending on the signs of the numerator and denominator. So let's just think about that. If we had a numerator that was, let's say, equal to 3, and a denominator that was infinitely tiny, super, super small, 0.000001, well, what we would have there would be a large number. And as that denominator is getting infinitesimally small as one can imagine, our limit would actually be infinity. Now for part D, imagine we had a numerator growing without bound over a denominator that was finite or infinitesimally small. That would produce a limit of infinity. So let's say we had a huge numerator over either a finite denominator or something that's unbelievably tiny. If you have that, you're going to be going to infinity. It might be negative infinity, though. It depends on the signs of the top and bottom. And finally, if you have a numerator that's infinitesimally small over a denominator that's finite or growing without bound, that would produce a limit of 0. So if we do this and we end up with a tiny numerator over a denominator that's either infinitely large or even if it's just finite, either case, a tiny number divided by 5 will still be tiny, and as that tiny number gets infinitely small, the limit will be 0. And similarly, a number that's getting infinitesimally small over a number getting infinitely large, that's definitely going to be a 0. Okay, so let's go through these steps. Let's evaluate the limit as x goes to infinity of that quadratic over that linear. Okay. Now in method 1, let's look at the numerator. Say we've got a degree 2 numerator, and let's look at the denominator. See, we've got a degree 1 denominator, and let's factor out degree 1. Well, if you factor x out of the numerator, you're going to have 5x plus 2 plus 1 over x. And if you factor x out of the denominator, you're going to have 3 plus 4 over x. And if you distribute this back in, you'll see that we actually do end up with what's stated there. Now, if you do that, you're then in a position where you can cross out those x's. And now you can look at the limit of each one of those terms up top. You've got the limit as x goes to infinity of 5x plus 2 plus 1 over x over 3 plus 4 over x. And we'll look at the limits of these individually. The limit of this as x goes to infinity of 5x is infinity, because as x gets infinitely large, 5x gets infinitely large. The limit as x goes to infinity of 2 is just 2. The limit as x goes to infinity of 1 over x is 0, because in that little fraction right there, you've got yourself a numerator that's finite and a denominator growing without bound. And as we saw in a previous slide, that'll be a limit of 0. Underneath, you've got a limit as x goes to infinity of 3. Well, no matter if x goes to infinity or where it is, 3 will always be 3. And you've got a limit as x goes to infinity of 4 over x. And this goes back to what we said earlier. If x is getting infinitely large, 4 over x is going to be getting infinitely small. Okay? So what's happening is we've got this infinitely large plus 2 plus 0 over 3 plus something tiny. Now, something infinitely large plus 2 plus 0 is infinitely large. 3 plus something infinitesimally small is what we call finite. This number here, the numerator, is infinitely large. It's not even comprehensible. But the denominator is a finite value. It's essentially 3. That leads us to an answer of infinity. Now, in method 2, some people, half the people do what we just did there, which is where we factor out the smaller degree, which in that case was degree 1. But the other half of people factor out the larger. So what the other half of people do is they'll factor x squared out of top and bottom. Now, when you do that, you end up with this expression, and underneath you end up with this expression. And if you don't believe me, you can actually distribute. X squared times 3 over x is 3x. X squared times 4 over x squared is 4. And it works for the numerator if you distribute the numerator as well. So once you make that factoring, you can actually just cross out those factors. And now we're going to be looking at the limits of each of these 3 individual terms in the numerator and 2 individual terms in the denominator. Well, the limit as x goes to infinity of 5 is 5. The limit as x goes to infinity of 2 over x will be, the limit is actually 0. The limit as x goes to infinity of 1 over x squared is also 0, because in both those cases you have a finite numerator over a denominator growing without bound. Underneath, you have something with a limit of 0 plus something with a limit of 0. So ultimately, you've got a finite numerator over a denominator that's infinitesimally tiny. And as that happens, as that denominator gets smaller and smaller and smaller, 5 divided by it will get infinitely large, and so the limit will be will be infinity. Okay, and that's what we're discussing here. So again, going through each of these individually, the limit as x goes to infinity of 5 equals 5. The limit as x goes to infinity of 2 over x equals 0. The limit as x goes to infinity of 1 over x squared equals 0. The limit as x goes to infinity of 3 over x is 0. The limit as x goes to infinity of 4 over x squared is 0. And we have a numerator with a finite limit over a denominator becoming infinitesimally small. The answer there is infinity. Okay, now we're going to use method 1 from now on. I wanted to show you that you can factor the larger degree out of both top and bottom, but from now on I tend to use where I factor the smaller degree out of each. Okay, so let's do this first question. The limit as x goes to negative infinity of this rational function shown here. Well, we see the degree of the numerator is 3 and the degree of the denominator is 3, so we can factor x cubed from top and bottom. We can then cross those out, and now we're left with the expressions you see there. Okay, now the limits as x goes to negative infinity of each of these is shown here, and the limit as x goes to negative infinity of each of these is shown here. And so what we end up with is a finite value over a finite value, literally just negative 6 over 2. And the answer is negative 3. That's the limit. Another way of saying that, and this is something that you would have learned in advanced functions, that function right there has a horizontal asymptote at y equals negative 3, because you might have learned that when you have a rational function where x's don't completely cancel out after factoring, then you're going to have a horizontal, and the degrees of top and bottom are greater than or equal to 1, and they're the same at the top and the bottom, then what you're going to have is a horizontal asymptote at lead coefficient over lead coefficient. And that horizontal asymptote is, in fact, the limit as x goes to negative infinity or infinity, depending what direction you're talking about. All right, so what if we have the limit as x goes to infinity of the expression shown here? Well, we can factor x squared from top and bottom, cross it out, and now we'll have the three terms up top and the three terms down below. Now, as x goes to negative infinity, um, 2, the limit of 2 is 2, plus a 0, plus a 0, so our numerator is 2. But our denominator, the limit as x goes to infinity of 6x cubed is infinity. And the limit as x goes to infinity of negative 4x squared is negative infinity. We can't add infinity and negative infinity to get 0 like we might with real numbers, but instead let's just think of the end behavior of the function 6x cubed minus 4x squared. And that function has a positive leading coefficient. Oh, and by the way, this one will be a 0. So basically underneath we've got 6x cubed minus 4x squared, and up top we've got a 2. So what we're going to do is we're going to say that this expression here, that 6x cubed minus 4x squared, has a positive leading coefficient and is degree 3. So that means as x goes to infinity, y goes to infinity. So we see that we're going to have essentially 2 over something growing infinitely large, growing without bound. And so we're going to end up with a limit equal to 0. Okay? Now you don't, if you give a solution where you show these steps right here, you don't even necessarily have to show the words there. But if you can show those steps, then you've shown enough. You don't have to go into the explanation on the previous slide, but that's there perhaps to help you understand what's going on. And this example here is pretty interesting. The limit as x goes to infinity of 3x minus 4 over the square root of x squared minus 3. Well, let's factor x from the numerator and root x squared from the denominator, okay? And let's just establish really quick why we say that the square root of x squared is the absolute value of x and not just x. If x is equal to 7, this is a bit of an aside, but if x is equal to 7, then the square root of x squared is x. But if x is negative 7, then the square root of x squared is negative x, in other words, positive 7. The square root of x squared will always be positive, but x itself isn't necessarily positive. So we have to say that the square root of x squared is the absolute value of x. That's a little bit of an aside. But it's important because what's about to happen is we're about to factor x out of the top and the square root of x squared out of the bottom. And we're going to have to say that the square root of x squared is the absolute value of x. And so it's important that we make that distinction. Okay? So when we do that, we end up with, as we shown on the previous slide, we end up with this statement here. Now, we know that the absolute value of x will just equal x because x is going to infinity. We're plugging in infinitely large positive numbers here. So if x is heading to positive infinity, x is taking on positive values. So we know that the absolute value of x is x. So now we can cancel out these x's here. Whoop. We can cancel out those x's that we see. And we can now say the limit of this term here is 0. The limit of that term there is 0. So basically we end up with 3 minus 0 over the square root of 1 minus 0. And the answer ends up equaling 3. Now what if we're going to negative infinity instead? Very similar process is going to occur. And there's just going to be a little change at the end. Okay, so similar process as the last question. we end up with this here. Actually, it's exactly the same question, except we just changed the positive to a negative as shown there. But now what we have to keep in mind is when x is going to negative infinity, the absolute value of x needs to be negative x, thereby making it positive. If x is a negative number, the absolute value of x must be positive, so put a negative in front of that negative number, and it'll become positive. Okay? So like it says here, it's explained at the bottom, we know the absolute value of x is negative x, so we plug that in. And now we can, instead of having negative x in the denominator, we call it negative 1 times x. We can cross out the x's as shown here. And now we can determine the values. Well, we know this will be a 3, that'll be a 0, that'll be a 1, that'll be a 0, but we still have this factor of negative 1 that we need to consider. And so the answer is negative 3.